Which of the following is not formed as an intermediate during the reaction shown below? So we need to first determine what this reaction is that we are looking at. And so we see that we are starting with a ketone, and we're reacting this with 2 equivalents of alcohol, HCl gas, so that's a nice dry acid catalyst, and we are forming something that looks like a diether. So when you have these 2 ether bonds to the same carbon atom, this is known as an acetal. So the carbon atom of that acetal is in the same oxidation state as the ketone. So these acetals are often used as protecting groups for aldehydes and ketones. And we will see that in another example. So here we are focused on the mechanism. And I'm going to warn you, this is a long mechanism to draw. I did promise you during class that I would draw it, so I will. But before I get to that, let me give you the fast way to get to this answer if you don't want to draw the whole mechanism. One thing to notice is that this is acid catalyzed. And so we have talked about acidic conditions many times in this class. And we have said that when you are under acidic conditions, you cannot form a strong base at any point in your mechanism. So a strong base will not form at any time because it's just not compatible with lower pH values. So what we typically see when we have acid catalyzed processes is we see positive charges, we see neutral charges. We don't see negative charges unless it's something like the chloride ion, which is essentially a neutral ion. So if we take a look at our options here, we've got something that's protonated, that looks reasonable. Something that's neutral, that looks reasonable. Another species that's protonated, that also looks reasonable. A negative charge on oxygen. This is a strong base. This is not compatible with acidic solution. So this definitely, without even drawing the whole mechanism, we're not forming that in acidic solution. So that means that if you want to just get to the answer quickly, we are done. All right. But if you want to see the entire mechanism of how this forms, stick around. We're going to draw it all now. So what we want to recognize is that when we've got HCl in methanol, what we really have, and that's only a catalyst, we just have a small amount of this protonated methanol. And so that's going to be our actual acid. So whenever we need to add a hydrogen, we're going to use this one. And then we have a whole lot of methanol. So methanol would be used as the solvent. This is an equilibrium reaction. We want to drive it towards the acetal, so we'd probably use a lot of that methanol. So this is going to be our base and our nucleophile. All right, so when you've got an acid catalyzed process and a carbonyl, the first thing you're going to do is you're going to protonate the carbonyl. Because if we didn't protonate the carbonyl, we could get to something like this, and we just said that that is a no-no in this sort of solution. So the first thing that's going to happen is we are going to protonate the carbonyl oxygen. So we are going to draw our active acid species, which is that protonated methanol, and we're going to use it to protonate the carbonyl. Okay, and so this is going to get us to a tetrahedral intermediate. And I am going to, like the answers down here, use the abbreviation PH for that phenyl ring to make this a little less cumbersome as we draw out all the steps. Okay, so we've got a protonated carbonyl. Right. So what that does is that makes the carbonyl oxygen more electrophilic. And now it can react with even a fairly weak nucleophile like methanol. So the next thing that's going to happen is that methanol is going to attack the carbonyl carbon. And so we're going to get to a tetrahedral intermediate. Every step of this mechanism is reversible. So we'll form this tetrahedral intermediate. So we've added the methanol. It still has a proton attached, so we want to make sure we don't forget about that. Okay, and so what makes these acid catalyzed reactions so long is we've got to move a lot of protons around because we want to remove this proton. We want to actually protonate the carbonyl oxygen again because it's going to leave as water. So we are going to first remove this proton. So if we want a base, we have methanol. So we will use methanol. And so we will remove this proton. And let's see, actually, we already saw this intermediate because we were asking to go back to the question. We can see this intermediate is this one. So this was A. So that was definitely formed in this reaction. And now let's go ahead and see what our next intermediate looks like. So now we have this neutral tetrahedral intermediate, and that's the structure B. So our little quick shortcut so far is working quite well. And so we want to lose this oxygen that was the carbonyl oxygen as water. So the next thing I'm going to do is I'm going to add a proton to there. So again, I'm going to reach for my protonated methanol as my active acid that is in solution. So we will grab that hydrogen and give the electrons back to methanol. So now what we've done is we've set this up to be a good leaving group. And the next step we're going to see is going to look a lot like an intermediate that we saw in different carboxylic acid derivative reactions, where we saw a leaving group be kicked off of the tetrahedral intermediate. So that's what we're going to do here. So we're going to use these electrons on this methoxy group to come in and form a double bond and kick off that leaving group. And so this, I'm gonna flip this over. So don't let that throw you off. I'm gonna flip it over so I have the OCH3 at the top. And so here we've lost the water, we've got one of the alcohol groups attached, so we're getting kind of close. And we should also notice that this intermediate is C. All right, so we have definitely verified that we do form all of these intermediates, but we haven't quite formed the product yet. So notice that this looks a lot like what you started with, right? You've got what looks a carbon-oxygen double bond, and it's a positively charged oxygen. It's just that we don't have a hydrogen there, we have a methyl group, but that still means that this carbon is electrophilic. So we're going to do the exact same sort of thing that we did right here. We're going to take another molecule of methanol and have it attack this carbonyl-like carbon. And we are almost done, I promise. After we do this, we're going to be really close to the acetal, one proton transfer away. So let's take a look at what this gives us. I'm going to draw down to here. I did warn you that this was long. So really super close, right? And we added a methanol. So here's that methanol we just added. So we are only one extra proton away from this acetal, right? So we're just going to use another molecule of methanol to remove that hydrogen. And that gives you the acetal. And so notice this is all completely reversible. So you can form an acetal if you use an excess of the alcohol and a dry acid catalyst. And if you want to reverse the reaction and you want to go from an acetal back to your ketone, then you use aqueous acid.